finish our block 2 quiz. So start off with some calculator practice. Hopefully I got the answer correct. So you've got 120 watts per meter squared. So watts represents what SI units? Joules per second, yeah. So we know we've got 120 joules per second. So how many photons will be arriving? So we know that we've got joules per second, 120 there. We've got enough information here, I think, to work out the energy of a photon. So I've got energy divided by seconds, and therefore if I inverse my answer, I can say how many things are arriving per second. That makes sense? So start off by working out what the energy of one photon arriving. You remember the formula? Do you want me to write it up on
the equalization?
Yeah, but this one's got speed of light there, and so E equals H C over lambda. Yeah. One of the things you're going to notice with nanotechnology is that you can sort of like always do a sanity check in your answer. So here it's not necessarily clear in your head which way round I'm going to do my energy and do the watts, but we know it's going to be a big number. So if you end up with a very small number, you can pretty much assume that you just need to inverse your number to get the correct one.
What would the units of like energy be? This won't be electron volts, or will it?
It will be in joules.
It will be in joules, will it? Right.
It's that special one that you use where you plug it in, the weird one, which is something like 1.24.
Wavelength is not the one to use.
That tends to be used by people who do spectrometry and that kind of stuff. This is a physics question. Has anyone got a big number? Yeah. Okay, that's so first of all, let's look at how much energy we're associating with one particular photon. Notice we've got 10 to the minus 19 there, so that's the same order of an electron volt. So once I've got that, I'm going to put that in. Obviously it's going to be the watts divided by the energy of one photon. And anyone get that answer?
Yeah.
About 3 times 10 to the power 20. Alright guys. Okay. Calculate the wavelengths for the X spectrum. So again, similar question as before, but this time we want the answer in nanometers. So I do need that previous equation I mentioned. So E equals, tell me the number.
1.24.
Obviously, simple bit of transposition here. Let's say in nanometers, and in this equation, is it in nanometers or micrometers? Is it not milli? Watch out, I've got a killer electron volt here. David, you got some answers?
0.2 to 11 nanometers.
Well done. How about everyone else? Okay, so this equation is in electron volts. So we don't want to be converting our electron volts to anything. We're going to plug that straight into the equation. Obviously need to do a bit of transposition on it. And be careful with this one here, because we want to then get rid of our suffix and make it into 6,200. Okay. Everyone happy? So, 7 key features of a photocapacitor. Let's go for, first of all, you could mention the what it's named, the metal oxide semiconductor. Obviously, it doesn't, these days it's made out of metal. The metal regions need to be isolated by an insulating layer. There's going to be depleted regions when it's in operation. You're going to have minority, and the word there actually that would be a good buzzword to say for photocapacitors: minority electrons in the well. But we could generate electron hole pairs. The electrons and the holes will separate and accumulate, and light can then be converted into electronic information. So there's a mixture of obvious things, such as the name. If you was asked to describe them, so don't forget the obvious stuff, the name. Also what the application, what they're used for. And then for most questions you're going to have a buzzword, so I would say that they would probably have in the marking scheme, if the student uses the word minority electrons. And they would probably have in the marking scheme an accumulation of electrons and holes, I would guess. Electron hole pairs, just go for that for any device, write that down. When I come to think of it, the other thing is that I've marked at level 2 and level 1. I actually haven't marked on nano technology, but they tend not to have negative marking. But what I mean is that if the question was give me 5 key features and you write 7 down, they're not going to say, oh, you gave me 7 and I wanted 5. Provided they're kind of all relevant, then I would always try to go for a couple of extra ones. Okay. So if you say something blatantly stupid or wrong, then you could be in trouble. So for electronic paper, we had this for lunch. Did Quinn mention about the biostability?
Didn't.
Oh, we didn't, did we?
I didn't mention the bystander.
No, okay. So the elements can be switched from one stable configuration to another. Correlated surface, that's a statement, another sort of kind of statement of the obvious, I think. Yeah. So you'd have that in your head, I think. You'd probably maybe do a sketch of it. The liquid crystals can be aligned either vertically, and again, I think that would be something that maybe in an exam scenario you want to draw a sketch for little rods moving around. Okay, and just gone into more detail. Right. I guess I could put some applications down here. I haven't put applications down there if I was describing where it would be used. Yeah, so any comments? Polarization maybe? Talk about that. Okay, intrinsic conductivity. So we've had this 3rd time now. So let's see if we can knock off 5. So intrinsic conductivity, anyone from the audience? Say that again?
Naturally occurs.
Naturally occurring?
Already there.
Um,
You have to mess with
temperature dependent?
Say that again?
Temperature dependent?
Yeah, temperature return. Yeah.
So I'll generate a dark current.
Um,
Intrinsic.
Thinking of pin.
It's relatively larger band gap as
Okay, yeah.
compared to the dot. It's conductivities.
So that again?
Would we say that would we write the comparison between the dot and the intrinsic in terms of its conductivity?
You could take a chance and go for a negative statement like saying it's not doped, which I suppose was Angela's answer. Yes? No? Yeah. Naturally occurring. Not doped.
Yeah.
That's covered. Okay, so we'll go for that. Okay, what about 4 and 5? We're coming up with answers not on my list, by the way, so well done. Electron hole pair. Yeah, well done, yeah. So electron hole pair is going to come up somewhere in your bloody exam, isn't it? So electron hole pair.
You said that electrons and holes are equal in number.
Yeah, saying the same thing, but let's go for
Yeah.
that. Hopefully the examiner will take it to us. So I've got stating the obvious again. All the electrons in the outer shell are going to be, so we got that one, we got the fact that it's a thermal dependency. Again, stating the obvious. The electrons hop from atom to atom. And that the positive holes are going to be moving in the opposite direction to your electrons. The holes will have lower mobility than the electrons. We had the equal number of electron holes and holes and electrons, and we could state that they both contribute to conduction. But I think the fact that we mentioned hole pairs, I think that'd be a good one. Yeah.
One thing, if you could please elaborate, the mobility of holes is lower than electrons. How would the mobility of holes affect its conductivity? Obviously, mobility has a relation with conductivity, or mobile.
Do you remember there's an equation at the back?
Yes. Or which.
So you've got a different mobility value that you'd be putting in there.
I see.
Yeah.
Yeah.
I think it's not much difference, though, is it? Is it 10%-ish difference or something like that?
Yeah.
Okay, extrinsic. So can we get 5? Do a countdown. So extrinsic. So let's state the obvious.
Very low band gap and
Okay.
it's
Yes.
stuck in my mind.
Yeah, lower band gap than intrinsic. Yeah. Not on my list, but well done. Okay, another one.
The electron holes aren't equal in number. Yes. If you dope something with with phosphorus,
Is
you
that
get more.
fair? Am I having
But
that?
once they're excited, there would be movement afterwards.
Okay, so different numbers, holes.
There's a sentence in the book somewhere that says the thermal effects are much lower than the doping effect.
Sorry, say that again.
Am I misremembering? There's a sentence
you're
in the book that says the thermal effects,
Yeah, thermal effects.
Excita-
Yeah. That they're not
excitation
going
are
to
there,
be
but they're much
much
smaller than the
swamped.
doping.
Yeah, by the doping.
Um,
Number 4.
they have lower resistivity as compared
Yeah, compared to the
intrinsic.
intrinsic. It's kind of saying similar to things
Similar.
previously, but yeah. Number 5. We haven't stated the obvious, I think. I don't think we have.
It's got stuff in it that wasn't there in the
Doping.
beginning.
I don't think we mentioned doping. Okay. So, the obvious one is that we didn't mention doping. And therefore, by putting doping in, you're now controlling the conductivity. Again, another obvious statement. So, Angela's one that that conductivity will be swamped by the thermal effects. Again, more obvious stuff. But they could be N-type or P-type. The N-type could describe a bit like a metal, because it's additional electrons